Thank you, Eric. So I'm going to go ahead and talk about how you can understand the performance of next-generation multicores very quickly. And this is quite related to what Bengt was talking about. He said you can't get functional power and performance together, and I'm going to get two of those, power and performance, but not functional. I'm also going to talk a bit about how the same techniques that let us do future multicores are also very helpful for understanding performance on current systems and hardware. So to get started with this, what do we need to understand performance? Well, performance is a combination of two things: the system characteristics, that is the hardware that you're running on, as well as the application characteristics, that is how your application works with that setup. So if we take a look at some examples of system characteristics, here I've got two very low-level ones. I've got the amount of resources the processor has for the scheduler, and the amount of resources the processor has for registers. And we can take a look at different processors here. You can see two different generations of Intel processors. And across these two different generations, Intel has significantly increased the scheduler resources and increased the register resources a fair amount too. And you'd expect that this will speed up the performance of your applications. Now, if we compare this to an ARM processor, we can see the ARM processor has many fewer scheduling resources and a bunch fewer registers. And this would lead you to conclude that your application is going to run more slowly on an ARM processor than it does on an Intel processor. But of course, that depends on the characteristics of your application. So if we take a look at application characteristics, how sensitive is your application to scheduling resources, we can see it varies significantly. So in the case here of the first application, switching to the ARM processor might not hurt you a lot, because it doesn't really need a lot of these scheduling resources, while the second one might. Same thing for looking at the register resources. Here we see two applications with very different behavior. One of them gets a significant benefit from more register resources, and the other gets no benefit whatsoever. So which application you choose and which platform you work on are going to be very important for understanding performance. We can see the same thing if we look at higher level issues in the system. So memory latency, what's going on in the cache system. If we take a look at memory latency across these three, we actually see that the ARM processor has a lower latency in cycles than the Intel processors. Okay, maybe that's good for some things. But at the L2 level, the latency is much higher. Go to the L3, well, the ARM processor doesn't even have an L3 cache. And if we look at DRAM, we see two interesting things. The first is that Intel's actually increased the DRAM latency from one generation to the next. And the second is that the ARM latency is even worse than that. Now again, how much does this affect your application if you want to choose what platform to run on? Well, it depends on the behavior of your application. Here are two applications showing their sensitivity to latency. That is how much they speed up when they get access to a faster cache. And we see that one of these applications has no performance difference no matter how much cache we give it, whereas the other one has a significant performance difference. So again, how much does this application affect you depends both on the hardware you're running on and the application you're using. So if we look at this, we come to the conclusion that we've got a very complex interaction between hardware and software, and understanding this is a difficult problem. Okay, so this is complicated, it's hard to understand, but what if we could understand this? What if I could quickly tell you precisely how your program is going to run on a particular piece of hardware? What could we do with that? Well, we could pick the right platform. So you could go in and put these two things together and figure out what's the right platform for my application to meet the performance requirements I have. We could also go in and understand the performance of future platforms. If you're working with a vendor who's coming out with a next generation platform and you want to know how your software is going to perform, you could go ahead and model this. Put in the new version of that platform and figure out how you're going to do. We could also do more stuff in terms of optimization. If we can see what's going on here, we can go in and optimize the software. We can see which parts of our cache hierarchy are affecting us. Where can we put in optimizations? And we can also optimize the hardware. If you're building an SoC, why not go in and figure out what is the right set of latencies for your application? Really do effective hardware-software co-design. And of course, if we can do this all quickly, we can do design space exploration. That is, we can afford to now find the right combination of software and hardware for what we want. So if we could do all of this stuff, we could do great stuff for our complex systems. But in order to do it, we need a fast way to be able to look at all these different designs. So we need fast and flexible ability to provide us with insights about the performance. And this brings me to an EU project called ADEPT. And the goal of ADEPT is precisely this: understanding performance and energy in parallel systems. The ADEPT project has 5 members. 3 of these members bring application experience, both from high-performance computing and embedded. And 2 of the members bring modeling experience for modeling the performance of the processor and modeling the performance of the memory system. And the goal of the ADEPT project is to build a model. And we want a model that can give us power and performance insights for multi-core processors. So precisely the sort of thing I was talking about. How fast is my particular application going to run on this particular set of hardware? So let's take a look at sort of the overview of how this model comes together. We've got a model that's going to give us power and performance, and this model is built up of high-level models. So we're not going to do the detailed simulation that Bengt was talking about that's very slow. We're going to have high-level representations of what's going on, and this allows us to rapidly get results, so we can iterate quickly and explore the design space. In order to get your application into this model, we need to take your application, we're going to have to go in and profile it, and then we can use that in our model. Now, this profiling step is a one-time cost. You do a profile, and then we can go through and change the application parameters. So we can go in and we can choose a different system to model a wide range of systems and get the results out. So this is the flexible part of it. Now, we've got these flexible application parameters, and we've got a fast model, and what that allows us to do is design space exploration. So we can rapidly go through and take a look at a wide range of different configurations and figure out what the power and performance will be. So that's great, but power and performance, they're not really everything we want. We also want to be able to provide insight. So telling you just you run at this speed or use this much power isn't really helpful. We want to be able to tell you where in your program you're having problems or what part of your hardware you can change in order to get better performance. So the real goal here is to provide insight into power and performance. Okay, now how can we do all of this? How can we be fast, flexible, and accurate? So we sort of want almost everything here all at once. And I'm going to give you some understanding of how we build this model and how we obtain this. I'm going to go through three key components of the model. The first one here is how we do the processor pipeline. How do we model performance in the pipeline? Second one is how do we model the memory system? And the third one is how do we model the branch predictor? And I hope after looking at those, you'll have a feeling of how this comes together to give us a fast model that's actually going to give us insight into where the problems are. So let's take a look at modeling the processor pipeline. So to model the processor pipeline, we're going to take a look at what goes on in the processor over time, and we're going to measure it in terms of instructions per cycle. That is, how much work is the processor managing to get done in a particular time. Now, when everything's going really well, when there are no problems in the processor, we're going to execute at a particular rate. And this is the base execution rate of the processor. So if you've got an Intel processor, it's probably 4 instructions per cycle. If you've got an ARM processor, 3, maybe 2. But when everything's going well, you're going to execute at this rate. Unfortunately, things don't always go well in processors. Sometimes bad things happen, such as a cache miss. And when a cache miss happens, it's going to take a long time for the processor to get the data back. And during this time, we've got a bunch of instructions sitting there in the processor that are ready to execute, and we'll go ahead and execute those, but we drain out. We can't put more instructions into the processor until we get that data back. So we're going to slowly drain the instructions in the processor. The amount of work we're getting done is going to decrease for a while until finally the processor is going to stall. It's just going to stop sitting there doing nothing. And obviously, this is not good for performance. Now, when the data comes back from the memory, we're going to get the data back, and now the processor can start up again. And there'll be some period of time where we're speeding up, getting more instructions in the pipeline, and then we'll finally get back to that base execution rate, and everything will be great until the next bad thing happens. So perhaps we have a branch miss prediction. Now, when we have a branch miss prediction, it means we've got the wrong instructions in our pipeline. We have to kill those instructions and start over again. So again, we're going to have this gap in our execution rate. So this is the kind of model we're looking at. This is called an interval model. And as you can see, this allows us to predict the performance. We can look at the instructions that are being executed over time. It allows us to predict power. If we know how much energy each instruction takes, we can figure out how much energy we're using. And we need two different inputs in order to do this. The first is the architecture parameters. That is, what does the pipeline look like? What's the base execution rate? How quickly does it fill? How quickly does it empty? And the second one are the application profile. So from the application, what kind of instructions are you executed? How often do these cache misses and branch mispredictions occur? And if we put all this together, we get the ability to very quickly, with a lot of flexibility, model power and performance, but we also get insight. So if you look at what we have in this model here, we can see where the performance problems are. We can understand that this area right here, that is the cost of that cache miss. We can see for this particular instruction mix, for this particular setup of processor, what the cost of the cache miss is, and the same thing for the branch miss prediction. So we can begin to tell you exactly where you're paying the penalty for different things, both as a function of the architecture and the application. Now, let's take a look in the next two parts where we get this cache miss idea from and how we figure out if we're going to have a branch miss prediction. So when we want to figure out cache misses, we need to model the memory system. And to model the memory system, we're also going to look over time, but instead of looking at instructions, we're now going to look in terms of memory accesses. So if we look at the data that a processor accesses over time, maybe it accesses the white address, the red address, the dark red address, a bunch of addresses over time, what we want to know is for a particular address, say this one here, is this going to be a hit in the cache? Because if it's not a hit in the cache, our processor may stall. So we need to know which is going on. And to figure that out, we simply look at the last time that data was accessed, and we ask ourselves a question. In this period of time, has enough new data come through our cache to kick out the data we want? And if it's kicked it out, then it's going to be a miss, and if it hasn't kicked it out, it'll be a hit. So if you look here, you can see we've accessed 6 pieces of data in this time, but only 2 of them were unique. And if we know that, we can very rapidly answer the question. Well, if the cache can hold more than 2 unique pieces of data, it's going to be a hit. And if it holds less than that, it's going to be a miss. So pretty simple way of modeling this. And this allows us to model the cache misses. Now, again, we need 2 pieces of inputs for this. We need the architecture parameters. How big is our cache? What's the cache line size, replacement policy, sharing between cores, that sort of stuff. And we need something about the application. What is its memory access pattern? Where are these addresses that it's accessing? Now, one of the great things about this approach is we're using a statistical model. And the statistical model allows us to sample these accesses. So instead of looking at all of them, we can look at a teeny fraction of them, typically only 1 in 1,000 or 1 in 10,000 memory accesses, and still be very accurate in predicting what's going on. So that allows us to do things much more quickly. So from this approach here, what do we have? We've got another fast and flexible model that allows us to predict what's going on in the memory system, and it also gives us insight. So if you look at what I have here, I can trivially model any size cache I want by just changing that number up there and asking the same question again. That allows me to generate graphs like this. It allows me to see what is the sensitivity of my application to each level in the cache hierarchy, to the size of the cache hierarchy, and I can put that together with the interval model to get all sorts of information about how the memory system is affecting things. Now let's take a look at the third part here. How do we model branch predictions? So we saw that if you mispredict a branch, it's going to hurt our performance a lot. The approach we take here is a little bit different. We're not going to look over time. We're going to take 2 insights. The first is that applications have some sort of branch entropy. That is, if you look at all the branches in an application, some are very regular and easy to predict, and some are more random and harder to predict. And we can profile an application and learn what sort of branches it has. The second insight is that different branch predictors and processors handle entropy differently. Some are going to be very good at random branches, and some are only going to handle very regular branches well. And if we put the 2 of those together, we can build a model. So here's some data showing us the entropy of different branches versus how well the predictor does. And you can see we can build a model here. And the nice approach of this is we can describe a bunch of different branch predictors here. So increasingly better branch predictors simply look like steeper lines on this model. So with this approach, we can tell you how likely we are to have a branch misprediction, and we can do that simply by saying if a branch has this entropy from our application profile, and we're using this branch predictor, we can just put it into the model and find out what the likelihood of mispredicting the branch is. And this is remarkably accurate. So again, 2 different inputs, the architecture parameters, what size and what type of branch predictor, and then profile from the application, what is the entropy in that application. And when you put these together, we get another fast and flexible model that tells us about branch behavior, but it also gives us insight. We can go in and see which branches in the program are problematic. We can see which ones are going to respond better to which sort of branch predictor. Again, help the developer understand where the problems in the code are. Okay, so how do we put this all together in the ADEPT model? Well, the ADEPT model is going to have these models inside it. We're going to put in the application profile, and we've got the architecture parameters that somebody's going to choose what they want to model, and the outputs are going to be power, performance, and insight. To build up this model, we're going to base it around the interval model I showed you. That's the key thing that's going to give us performance and power, and we're going to feed that with input from the memory model, so we know when we have cache misses, and input from the branch predictor model, so that we know when we have branch misses. In order to make this all work, our application profile has to collect data for each of these models. We need to know which instructions we're executing, what the memory behavior of the application is, and what the branch behavior is. Then when you want to model something, you go in and specify the different parameters. Specify what's the microarchitecture, what processor core pipeline do you want to model, what sort of cache setup, what level of hierarchy, sizes, latencies do you want to model, and what sort of branch predictor do you want. And you put these together, and we can now rapidly predict power and performance. Now, as I started out, this is for multi-core processors, so there are a bunch of other parts of the model that aren't in here for dealing with synchronization, TLBs, and the like, and those, of course, require collecting other information as well. But the result of this is what we hope to achieve, a fast power and performance model that's going to give us insight into what's going on in a multi-core processor. Okay, so how well does this work? Let's take a look at accuracy. So here are some numbers for predicting performance. You can see a reference in a model run here. And across a wide range of different configurations and benchmarks, we've got about a 9% average absolute error. So we're getting pretty good accuracy for this very fast model. And if you look at modeling power, here you can see a wide range of benchmarks. Each benchmark is modeled for 3 very different processor configurations. And you can see, again, we're also doing very well in getting good accuracy out of this model here. Now, I've stressed a lot the idea of getting insight out of this. We don't want to just get a final number. We want to understand what's going on. And let me show you how we provide that sort of insight. So this is the output results that we're going to give you. We're going to tell you how the processor spent its time. Tell you how much of the time was spent in the pipeline, how much of the time was spent on branch mispredictions, and how much of the time was spent waiting for the memory. And you can use this by knowing where to target your optimizations. So if you saw something like this, you might think, well, how can I make this better? I'm spending all my time in the memory. The obvious thing to do to improve the memory system is put on a larger cache. Now, with our model, 1 second later, you can get the results. Hey, a larger cache didn't help anything at all. So what's going on? We're still spending a lot of time in the memory system. But a larger cache doesn't help us. What that probably means is the processor core doesn't have enough out-of-order capability to take advantage of the memory system. We're not getting enough memory-level parallelism. OK, well, we can check that out. Let's try a larger out-of-order core that can do more memory-level parallelism. Again, 1 second later, we get our result. It's 30% better. So by having this feedback loop here, we can go through and very rapidly iterate back and forth, figure out how to explore the design space, figure out where the issues are, provide feedback to the developer about what the interaction between their platform and their application is, and give them this insight as to not just what the final performance and power is, but which part of the system is having the issues. OK. Now, this is all great to put together a bunch of slides here, but we're going to go off and do a demo now. And I'm going to introduce Dr. Trevor Carlson, who is a researcher at Uppsala University. And he's going to actually show you this model running. And Trevor did one of the fastest detailed timing simulators in the world, Sniper. And he did that as part of his PhD work. And what he's going to do now is he's going to take his really fast Sniper simulator, and he's going to race it against the ADEPT model that I just showed you. So let me go ahead and hand it over to Trevor.
Thanks a lot, David. Okay, let's make sure everything's working here. Are we good? Yep. Okay, so what do we have here? Well, David talked a bit about the fastest simulator, the fastest performance simulator. And at the time I developed it, it was pretty fast. Of course, that was 5 years ago now. So technology has advanced at the same time. So what I have here is 3 screens actually. On the right here, we have the Sniper simulator. And on the left here, we have the profiler. So what I'm going to do is I'm going to start this profiler here, and I'm going to start the Sniper simulator. OK. So what we have happening right now on the screen, on the right side, we have Sniper taking your application, taking your binary that was compiled for real hardware, and it's running it in a detailed timing simulation. So what that means, it's looking at for the single point, a single cache configuration, a single branch predictor configuration, a single processor configuration. And it's running that on the right-hand side here. Now on the left, at the same time, I'm doing I'm using the ADEPT tool, and I'm doing the first step of the ADEPT tool, and this is the profiling step. So what we're doing is we're doing this, the profiling of an application where we run the profiler one time, and we collect this information that David was talking about, which is the information about the memory hierarchy, the information about the branch entropy, and also other information. Oh, look, it's done. Well, that's good. So now we've just profiled the application. And over here on the right, Sniper is still going. OK, but let's see what we can do now with this. Let's run the analyzer now on that profile. OK. So it does some calculations, and it pops up this screen. Ah, look. So what we see here, we have two large pieces. The red piece is this memory piece that David was talking about earlier. So in this case, we saw instantly, look, this application spends a lot of time in the memory hierarchy. In this case, it spends a lot of time in DRAM and waiting for DRAM requests, and not too much waiting for the core. Let's take a look here. Sniper's still going, but it'll come back soon. Okay, so let's look at something else. Let's look at another configuration and compare the result from a different vendor. So what we have here is a faster processor and also a different cache configuration. And so in the case on the right, which is the example we just ran, we see that we're able to perform much better because of the cache configuration is able to hold the data locally, and it doesn't really need to go to DRAM as much. So this is an interesting insight. Now the problem that comes up is in my case, say I'm building a new machine. And I really like that processor on the left because it's really affordable. The processor on the right is great, but it's a little bit too expensive. It's a little bit outside of my budget. So what I want to do is I want to see if there are other configurations of that first processor that maybe can perform better. Oh, Sniper's doing well. So what I'm doing now is I'm quickly running 5 or 6 simulations, and these are these analytical modeling steps. And what happens now is we're looking at all the different parameters for cache sizes, because I know that vendor has some options in the here we go. I know the vendor has some options for different caches, and now I can quickly do a profiling run and say, well, if I use a larger cache configuration, then maybe I can do much better and I can approach the performance of that other core that I really was interested in. And in this case, we get very close by doing those 6 simulations. And I think Sniper should be done. Ah, yes, I left out one piece of the puzzle. So Sniper only simulated 1 configuration just now. It just finished. But those other 6 configurations, it still has to work on those. So it's starting up all the extra cache configurations now and branch configurations. It's going through those, and it's going to have some fun. So that is the demo. And thanks a lot. Pass it off.
So do we have questions?
Yeah.
So this is Christos Kosirakis. He's going to talk after lunch, and he has developed the world's fastest simulator, I think, actually, right now. No.
Great talk and great demo. So the basic question that I always have about tools is the following. Every tool has, some amazing use cases, and it's the best tool for something. But it's really good to also understand when I should not use a tool. When is the wrong tool for the job? So what are the kind of experiments or the kind of things that one may imagine where your tool is not the right one? What is the quick check that should do to basically say, is this the right tool for me or not?
So this would be the wrong tool if you were a hardware designer and you wanted to design the next detailed part of a branch predictor. Because what this tool does is it profiles and gives you, here's the general performance of a branch predictor. Now let me predict this. What's the overall performance going to be, but not the detailed corner cases. And so if that's what you're focusing on, this isn't going to get it for you. This is going to tell you for your application to within 10%, here's your performance. But if you really care about what happens in that, plus or minus a few percent around that error, then we're not going to be able to get that for you. So this is useful for people who want to say, to the first and second order, what's the performance change I want to get? But if you won't care about the third order effects, this is not going to capture it for you. That would be the big thing I would give you on that. Trevor, did you want to add anything?
Yeah, each step of the process, right, gets you more and more detailed. And even Sniper, it has a level of detail that's quite interesting, but it trades off some of that detail for speed. And other simulators like ZSim do the same thing. So as you get closer to real hardware, you need a more detailed simulator. And this is maybe one of the furthest steps, right, to give you the overview and to give you the insight.
Hi, Jakob Lunge with Ork Group. So I was just curious about what will the end game of this project be? Is it being turned into a commercial venture, or is it being developed just to be open?
So the immediate results of this are first for the partners in the consortium for the project, and we need to figure out how we can make this available, whether it makes most sense to commercialize it or to make it open source, but we want this tool to be usable by people.
Bernd Moore, Uli Supercomputing Center. So you showed the, the application use case where if you try, I want to get inside, if I change my hardware, how I get better. But I mean, typically I have a barter system and I have my software, and then I want to get inside what I need to change in my software. I guess you still can do it, but then I have to do the usual thing. I have to think, oh, like, let's access my data in a different thing. I rerun your sampling, and I can find it out. So basically here you're not speeding up as much because I still have to rerun the whole thing again, and you cannot use your fast simulation, just if I understood it right. Or do you have other parts in your process which give people a hint what they have to change in their software to get better?
So I would say two things about that. You're absolutely right. If you want to change the software and iterate on the software, you have to reprofile after each step. And we do have a bunch of knobs we can turn to affect the performance of that. What's the level of detail you sample at and the like. So we can definitely speed that up. But the fundamental point you make is absolutely true. You have to resample. A lot of the insight that we can provide, however, comes from running the model multiple times. So if you want to know how important is it for me to fix the cache for this particular part, you may need to run 15 or 20 different models in order to figure out how does the sensitivity of the cache around there vary. So a lot of the benefits we have from being able to quickly model are still applicable, but you're absolutely right. When you go in and change your software, you're going to have to reprofile, and we can do accuracy performance trade-offs there. But the main benefit that we're touting is the ability to run the model quickly.
Trevor, can I sneak in a speed question here as well, since I asked Bengt that? So this is clearly a prototype you're showing here. What do you think is the slowdown of the reasonable sampling, this sparse sampling kind of tool?
In X, you mean?
Yeah.
Well, the prototype right now might be around 100x slowdown, but we're working to improve that performance, right? So we're looking into different techniques to maybe make this, or so to improve it from, you know, we're trying our best to make it something that you can run on a native hardware with very minimal slowdown. We're not there yet, but that's sort of our goal. And now, can we use other techniques? Can we use things like hardware virtualization to help us to get there? And that's what we're hoping to do.
I was going to ask about...
So what's your name and affiliation?
Stuart Mendelsohn Tenetech. I'm interested to know about applying this maybe to semi-custom. Do you think that would be interesting? FPGAs, things like that? Would that be a valid approach?
If the parameters you have in your semi-custom design are the sort of parameters we're looking at in terms of, you know, out-of-order pipeline with the sort of general outline that we have and the memory hierarchy with the general outline we have, of course you could apply it. Now, with an FPGA, you have sort of the added complexity of you start affecting your clock cycle time very easily. We don't have that built in. You could easily imagine building that into the model. But the requirements for using this model is it has to look significantly like the sort of out-of-order processor systems we have today.
Yeah, but that said, I would say that one of the things we're looking at now, so the graphs we showed were whole system, whole application runs. So once you start looking at a per time basis, you start to get a better understanding of the phase behavior of the application. So what you can do, a methodology, a potential methodology could be to look at the phases of your application and look at which phases are particularly poorly suited for your core, right? And then you can take those and you can say, maybe these are the ones we need to offload. And this was also mentioned earlier by the other Trevor when he mentioned that, anyway, so these are the kinds of things we can look at, right, and we can do.
Kostis?
Kostis Agonas, Uppsala University. I missed a bit the connection with multicore. Can I, simulate my i7 processor there?
So the goal of the ADEPT project, as David started with saying, is multicore. And that's the goal for both performance and for power. And so, of course, this is also a research project, right? We are currently working on all of the multicore pieces, and we're putting them together now. So that means that we have something that we're using to simulate and estimate performance of multicore.
So to translate what Trevor said, the demo for the full multicore wasn't ready for today. But yes, absolutely, and this whole thing is built with that in mind. And sorry, yes, and power, of course. Yes.
Any more questions?
Alexandra from Uppsala University again. So the model, in order to predict and understand performance and power, is it decoupled or is it specific to the simulator that is in use? So can it be embedded easily, integrated easily in other simulators?
Yeah, so as I gave you a feeling for sort of the types of inputs that are needed, both in terms of the parameters for the architecture and the profile from the application. As long as you can provide that sort of input to the model, you could run it from anything you wanted to. So yeah, you just need to be able to provide that sort of input.
So how do you get the right power input, for example, that's relevant today? It's very hard to get those numbers.
How to get the right power?
Power parameters in your models.
Oh, I see. So you're saying, how do we take the runs that we have using the model and actually get accurate power numbers?
Or how you know that this is accurate compared with existing systems?
Well, so one of the partners in the consortium here, Alpha Data over here, they are the ones, they've actually built hardware to measure specific machines. And what we do is we run and we compare to what they do. And that hardware also allows us to calibrate our models. So we can go in and measure on the system what is the cost of different instructions in terms of energy and put that into our model in order to get the accuracy that we want out of that.
So the idea is to start off and measure both the small, the micro, the nano level, as well as comparing that and putting that together for the larger system and looking at the entire thing.
So Håkan Seffer from Intel Corporation. So I have 2 short questions. The first one is, are you able to do full system stuff, or is it only user level? I know Sniper originated from user level stuff, right?
Yeah.
So, and the second one is, what about if you want to test somewhat different architecture, something like what Transmeta did with code morphing and stuff like that? How would that fit in? Would you be able to do that? Or?
So the question about full system, the model we have now includes the things that we showed you, the memory system and the processor and the branch predictor. We don't include things like network and disk and the like. If you wanted to include them, it would be a fascinating project to build similar models, and I think you could do that, but we do not currently include those in there. If you wanted to do something like Transmeta, where you're changing the code, you're adjusting, dynamically adjusting, you need to make sure that you have the right application profile information. If your processor and your application are changing over time, you'd have to extend this to be able to take different parameters over time and simulate them. I think you could do that, but as I said, this model is based on the idea that you basically have an out-of-order processor system that looks like the ones today, and as you move further and further away from that, the assumptions under the model might be less accurate.
Right, so back to the first one. So what I meant by full system is, well, yeah. Well, do you also do supervisor stuff? So, like if you have like an database, do you get the operating system part of it, which is a major part, right?
Right. There's nothing fundamental to full system versus non-full system. Some of the prototypes, like the prototypes I showed here today, is user land, right? But the models all apply to full system as well, right? So what we're working on now, and we've got prototypes in the lab, these use full system simulation information, full system information, right? So there's nothing fundamentally different about the.
So what Trevor's talking about is we're working on using virtualization to capture the application profiles. And once you do that, you can now capture profiles which include the entire OS running as well as the application, and then you'd be able to model both of those parts. The question, of course, would be capturing the right parts of time in order to get a representative sample.
Okay, thanks.
That's it for questions. So thanks again, and let's break for lunch.